Hi everyone. In today's video, we're going to be breaking down how Claude research capabilities work. It's very good and interesting to learn from a big tech company or a big AI company like Anthropic and Claude, because in my opinion, they actually built one of the best AI agents in the world, which is Claude Code. So Claude Code has all the aspects of any AI agent that you can think of. It has memory, it has tools, sub-agent, parallelism, MCPs, you name it, skills they introduced also recently. So it's very actually interesting to learn how they think, how they do their architecture, how they do their maybe prompt engineering, how they do their evaluation, which is also very important. So a multi-agent system consists of multiple agents working together. Our research feature involves an agent that plans the research process based on user queries and then uses tools to create parallel agents that search information simultaneously. So here they're breaking down the architecture. Really simply, it's just an overview. You have like a lead agent, kind of, and this lead agent will spawn multiple sub-agents to research the information based on the user query. Okay, so what are the benefits of multi-agent systems? So as I said, multi-agent systems, they introduce complexity. They may be over-engineering sometimes. Also, your state and context is going to be scattered across multiple agents and multiple parts in the code base and at runtime. What are the benefits of using multi-agent system to begin with? When you're searching or doing some research for a topic, you don't just like usually follow a linear execution path. Usually it involves looking into multiple sources and then deciding whether to go deeper based on what you found in that source. You can think of it as a tree of decisions that you make along the way to either go deeper in some topic or like to stop and choose another topic, or to stop and grab this information and like conclude your search. Okay, so the essence of search is compression. This is also a very good point. When you're doing research in general, you are compressing a huge corpus of information on the internet and you are distilling this information and trying to get the most out of it. Okay, when intelligence reaches a threshold, multi-agent systems become a vital way to scale performance. When you have a single agent, let's say this agent is AGI, right? Like it's basically the most intelligent agent in the world. The next step, after you reach that stage, you don't expect this agent to be able to solve all tasks in the world. Even though it has like a very high intelligence, there is a limitation. And the next step to improve that or like to scale this is to use multiple of them in general. That's how people think about the future. The future is going to have AI agents more than humans, and they are running in parallel, executing tasks. So it's not just like a single AI agent that solves all humanity's problem. Individual humans have become increasingly intelligent over the last 100,000 years, but a single agent or single individual cannot solve all humanity's problems. So you cannot expect like Elon Musk by himself to solve all the humanity problems. Actually, how human development works is that it's collective. So it's basically, it accumulates over the years. The overall society intelligence grows exponentially. So this is basically the analogy that they're using here. Basically, multi-agent system provides 90% performance enhancement based on the internal research evaluation that they have at Claude. So using Claude Code as a lead agent and Claude Sonnet as sub-agent outperformed single Claude Opus agent by 90%. So this is very significant. Okay, so why multi-agent systems are better in this case? It's mainly because they consume more tokens. So one agent cannot consume tokens or read information or read data from the internet as fast as multiple agents in parallel running. So that's basically the main point here. So the downside is the budget. So because it consumes more tokens, it becomes more expensive. And here they say that basically having multi-agent system is 15 times more expensive than having a chat system. And having an agentic system in general is 4 times more expensive than just having a chat mode. So yes, it also comes down to the viability of the problem that you're trying to solve and how well multi-agent system suits it. It's actually a valid argument in some cases. For example, like coding, when you want to write code, you don't want parallel agents. You want a single agent that is intelligent enough to take your task, break it down, and translate it into code. So now let's talk about the architectural overview. Here I explain it for you. So first the user query comes in, then we have the lead agent. The lead agent will then write first a plan and save it into an external memory. And also it will spawn the sub-agent, so it will invoke the sub-agents to perform those specific queries. Let's take this example. What are all the companies in the United States working on AI agents in 2025? So this query can be broken down into multiple queries, and those queries will be directed to the agents. For example, one agent will search for all companies, another agent will try to search for specific company to get their information, like website, name, whatever. And those agents, they then return back, so they do the web search, and then they return the result back to the main agent. Also include the citation based on the documents that have been returned by the sub-agents, and it will then return the final answer to the user with the citations. Also, as I told you, the external memory is really important in this case, because as the sub-agents reporting back their results to the main agent, context window is going to grow. And the context window limit for Claude, it was 200,000 tokens for Claude Opus. Therefore, when you returning a lot of information, a lot of data to this 200,000, the plan might get lost. That's why we save it in a separate memory source. Here, they also make a comparison with traditional RAG. So how this is different from RAG. So how RAG works, it takes the user query first, and then it tries to find the similar documents semantically to the user query, and then it returns these documents. But this approach actually dynamically searches the web and uses interleaving thinking. Interleaving thinking means that the agent will call a tool, will get back the result, will think and reflect about it, and it will decide whether to do or to perform a deeper task. We took a look at the architecture. Now let's take a look at their prompt engineering techniques. I actually personally don't like prompting. The main reason being is that LLMs are undeterministic. The output will depend not only on the prompt, it will depend also on the context of the conversation, and it will also depend on the specific query that you're tackling. If you start changing the prompt a lot, you introduce like a lot of degrees of freedom, and therefore you're going to lose the systematic way of improving your agents. That's why I look for other ways to improve the agent by like re-architecting or introducing tools when necessary and connecting the tools to the agents in a better way. But here actually they tell you the importance of prompt engineering, and they also tell you about the techniques they used for prompt engineering. So the first lesson is that think like your agent. So instead of trying to improve the prompt by looking at edge cases and then telling the agent to say, when you see this, answer like this. When you see that, answer like that. Avoid that, like don't do that. Instead, think of a mental model of your agent. So how your agent is going to tackle the problem from a broad perspective. Try to think like an agent and build a mental model. So this is how they call it, mental model for the agent. The second thing is to teach it how to orchestrate and delegate. So obviously when you have a multi-agent system, you need the lead agent to orchestrate the agents well. So in some cases, for example, here they said, if you give your sub-agents vague instructions, the sub-agents will duplicate work. Different agents are going to have the same results, or they're going to try to tackle the same problem if the problem is vague or the same problem is given to multiple agents. That's why how they teach the agent to draw borders between the instructions or the queries that are being assigned to sub-agents. The third lesson is that you need to scale efforts to query complexity. What they do is they do something like this. For simple queries, they tell the lead agent to assign only a single agent, like for simple queries, and also they tell it to use around 3 to 10 tools. And for complex queries, it's actually allowed to use 10 plus sub-agents in parallel execution. So the fourth lesson is the tool design and selection are critical. When you have a multi-agent system that all it depends on is tools, which is like searching the web, basically, you don't want your agents to basically miscall a tool. If the context exists in some application like Slack, and then you have a Slack tool, and then you have a Google search tool, if your answer exists in Slack, but then the agent decides to use the Google, then it's going to fail. So that's why they said that they provide detailed descriptions of the tools, and they tell it exactly what every tool does. So they also tell the agent to look at the tool arguments and look at the query and try to classify the tool in the best way possible. So the key here is just to write very detailed and accurate description of the tool and give that description to the agent. Also, they let the agents improve themselves. So they have this autocorrective or iterative prompt adaptation technique, or they build a tool testing agent that go execute these tools, find or identify failing modes, and then tries to improve the prompt. So it's like self-improvement kind of agent. And this, they said, it decreased the overall execution time to answer the user query by 40%. So this is actually significant. Now, they also have a technique of start wide, narrow down. So it's like a breadth first search. So first, it's like the human do. When you do research, first you kind of skim through the sources, and then whenever you want, you just like go deeper on the topic that you want. So you first start broad, and then you go deeper, and they actually like describe this to the lead agent and also to the sub-agents to implement this concept. So they also introduce the extended thinking mode. So they actually produce visible thinking tokens, and this thinking mode actually improved the results in general. The last lesson now is parallel tool execution. So the parallelism is very important. Not only the sub-agents execute in parallel, but also within the sub-agent, the tools also execute in parallel. So it's like extensive parallelism, and this also drops the execution time. Here they say like 90% for complex queries. So these parallelism implementation actually cut down the research time by 90%. So this is very significant. So now let's talk about the evaluation. Actually, evaluating multi-agent system is actually tricky because there are a lot of points for failure, and there are a lot of degrees of freedom, a lot of things that could go wrong. So let's go through them like one by one. Start evaluating immediately with small samples. So here actually is very interesting. We think that like to improve an agent or like to improve an LLM, you probably need a huge data set of like thousands of samples of how the system works in order to improve the agent. But at early stage, when you have a lot of room for improvement and when you have a lot of low-hanging fruit that you can solve, actually a very small set of samples, as small as 20 queries, can provide a huge boost of improvement from like 30 to 80%. It's important here to like start small first, identifying the big things that you need to improve before going deeper and deeper into your evaluations. The second thing is LLM as judge. So you actually let the LLM evaluate. It's kind of similar to the like iterative prompt improvement, but here you have LLM as a judge. So you run your experiments or you run your simulations of the queries, and then you let an LLM take a look at the results and judge this result. So now the human evaluation. So when you have LLM as a judge, who's gonna judge the accuracy of that LLM? You then need another LLM, and for that LLM you also need another LLM. So the truth is, you cannot basically have a 100% accurate answer. And in research problems, you mostly can afford to have it because the human or the user will also do the fact checking at the end. But also you want to like front load that as much as possible. And also they do that with human evaluation. So the people also testing the agents for edge cases. So in our case, human testers noticed that our early agents consistently chose SEO optimized content over high quality sources. And therefore adding source quality heuristics to the prompt helped resolve this. So basically, they said that the human testers actually helped to identify some of the issues. So now let's take a look at the production reliability of these agents and what challenges will you face when deploying it into production. So the first challenge, agents are long-running programs where they're gonna run and they're gonna search the internet like for maybe minutes or tens of minutes, and they're gonna come up with an answer. And during this period, a lot of errors can happen, right? Tool execution, formatting errors, context window stuff. A lot of errors can happen, and you need to have a very safe way to handle gracefully these errors. When an error happens, instead of restarting the whole execution from scratch, you actually save every successful step in a checkpoint, and then you restart from that checkpoint. Right? And you save all the state in that checkpoint and you resume from that. So you don't lose any time, or you don't also lose any progress that you have made. So this is the first issue that they faced, which is logical. First thing is that debugging. Debugging, as I told you, debugging AI agents can be really difficult because they are undeterministic systems. You need to understand that. Even if the prompt is exactly the same, the context at some point is going to be different, and the agents are going to like behave maybe unexpectedly, right? To mitigate that, you need some system for debugging. For every failure, they track what calls have been called, how the orchestration structure patterns been between the sub-agents, and they try to identify points of failure for that and try to fix it. And the third thing is a deployment in flight agent. So the agents are running in the deployment. They cannot immediately replace all the agents that are currently live, right? Because like some of them are running, so they do like some slow rollout. Synchronous execution, it creates bottlenecks. So because the lead agent spawns multiple sub-agents, you want to do that as in a synchronous way, so that when the sub-agents are running, you can, at any moment, you can spawn up a new sub-agent, or you can like conclude the answer to the user when it's ready. So you want to do all these things asynchronously. Yeah, actually that was it. We have learned how they built their multi-agent system. It's actually very interesting because here they say that 90% of the work is after the system has been built. So building the system is actually only maybe part of the work. It's not the most difficult part of the work, but the most difficult part of the work is evaluation, iterating, and deploying it in production. So thank you so much for watching. See you in the next one.